Hello everyone, welcome to this session on RTL and synthesis, RTL coding and synthesis. So the last discussion we saw about the coding of for loop and for generate constructs in Verilog, and we are going to see a lab now to show a demonstration of how these looping constructs and for generate constructs are very helpful in generating uh, a very complicated hardware also in a very simple elegant way. Okay, so first let us look at our mux. I'm going to show you the example of a mux here. So mux, the lab files are present in the folder called Verilog files, and the file name is mux underscore generate. This is the file we are going to use for this lab. Let's look at this code, what it is exactly trying to do. As we discussed in our theoretical session, the same thing is what we have written as a code here. So if you see, the module has input called I0, I1, I2, I3, 4 inputs. It has 2-bit select lines, select of 0 and select of 1, or rather select of 1:0. Select is a 2-bit signal, and it has an output. It's a 1-bit output. Now what we are trying to say, we are making a wire, we are making a bus here. Internally, we are making this as a I underscore int, a bus. What is I underscore int? I underscore int is nothing but having these wires. So this I am calling it as I underscore int of 0, I underscore int of 1, correct? This is how the bus is formed. I underscore int of 2, I underscore int of 3. Now what am I doing here? Always at star, I have declared an integer called k. I formed this bus. I'm declaring an integer called k, always at star. In the discussion itself I told you, for generate and for are two different things. For loop will always occur within always. For generate will always occur outside the always. Please keep that in mind. For generate is going to replicate a hardware. For uh, is going to be a very simple way of writing a hardware, of writing a very big hardware. Okay. So let's look at this. For k equal to 0, k less than 4, k equal to k plus 1. So now look at it. If k is equal to select, now select is going to take only one value. Select is a 2-bit signal. So select is a 2-bit signal. It can take what? 4 values, 0, 1, 2, 3. These are the 4 values the select can take. If k and select are matching, this k is going to loop. So first k is going to take a value called 0. When k is 0, if select is 0, y will be assigned a value of I int of 0. I int of 0 is nothing but I0. Correct. So what effectively you are saying is this may come here, or this may come here, or this may come here, or this may come here, which is controlled by select. This is exactly the function of 2 cross 1 mux. Correct. This is nothing but this. Here I0, I1, I2, I3, and I have cell 0 of 1, the output y. If select is 0, 0, output is I0, correct? Whatever is the value of select, that corresponding input is selected as output. That's exactly what we are seeing here. Correct? This is our understanding from this code. Let us look at this code let us simulate this code and see what it is going to generate. Okay. So to simulate, what we will do, we call iVerilog, and as our naming convention goes, the TB will be the same file name prefixed with TB. So the mux generate is the file name. So the TB is going to be TB underscore mux generate.v. So it's done. So /a.out. We will generate the VCD value change dump file, and I load that value change dump file in GTK mux generate.vcd. So let's see. So these are my signals. So this clock, reset, and all are test bench signals. Don't worry about this. I0, I1, I2, I3, select, and Y. Correct? I don't need reset. So these are my signals. Let us plot these signals and see what happens. Now exactly see what is happening. When select is 0, my I0 is what is being sent as output Y. When select is 1, the input, let me put this in different color so that you can compare it. So I'm going to put color, put orange for this. I'll put, let's say, yellow for this, and let me put red for this for sake of understanding. So now if you see here, this is exactly following the green pattern. This is exactly following the orange pattern. The output here is exactly following the yellow pattern. The output here is exactly following the red pattern. So if you see here, the select line is 3. So it's following the red pattern, which is I3. The select line is 2. Correct. 1 0 is 2. Correct. If you want, we can change the radix of this also to decimal. So you can see the select line is 2. So 2 is I2. Correct. The input corresponding to the select of 2 is I2, which is yellow. Exactly the output is following the yellow pattern. Select 1. Select is 1. So my I1. So exactly my output is following the orange pattern. My select is 0. So my input is following, output is following the I0. And that repeats till the end of simulation. So this is exactly what we saw. Now you may ask me, what is the speciality of writing this code this way? So what exactly did we achieve? Now look at this code. For sake of argument, let's say for example, if I write the same code using a case statement, how it will look like. I think we discussed this in the class also, right? So if I write the same code using the case statement, it will look something like this, correct? Case of select 2 tick B00, y is equal to I0, 2 tick B01, y equal to I1, 2 tick B10, y equal to I2, 2 tick B11, y equal to I3, end case, correct? That's it. This is how the code is going to look like. Now if you see here, this code, let's say for example, instead of a 4 cross 1 mux, you want to write a 16 cross 1 mux or a 256 cross 1 mux for sake of argument. This code will become very complicated. You have to write 256 statements or 16 statements. 4 tick B0000, 4 tick B0001, 4 tick B0010. Like this, you have to keep on writing till 4 tick B1111. Here you have to write 8 tick B000000 to all the way till 8 tick B1111. This much you have to write. This is 256 lines. 1024 cross 1 mux means you have to write 1024 lines. Here I am least bothered. You want 1024 cross 1 mux? Fine. I will create a 1024 bit bus and this code 1, 2, 3, 4 lines of code. This 4 lines of code is going to take care of anything. You want to get a 256 cross 1 mux? You make this, just edit this to. Of course, when I do this, of course, I need to supply the input also corresponding to that. So I should have a 256 bit input. Correct. Of course, that input should be there, which is anyway going to be there. The fact that you are creating a 256 cross 1 mux, you will not do that without having 256 inputs. Correct. So that is there anyway. But you see here, this is going to be just 4 lines. Whether you want to create 256 cross 1 mux or you want to create 4 cross 1 mux, doesn't matter. The code remains the same. It's going to be very elegant way of writing the code. Clear? So this lab as an extra I'm not going to synthesize this. I want you guys to experiment with this synthesize it and simulate that waveform also and check whether the synthesized waveform also is giving this, and synthesize this code and check the expression for y is indeed matching the 4 cross 1 mux expression. That I want you guys to try it out as an assignment. Okay, let's go ahead.